Welcome to our introduction on the power of pressure. Pressure is a fundamental force in our physical world, constantly surrounding us. From the air we breathe to the depths of the ocean, pressure plays a pivotal role in shaping our environment. Harnessing the power of pressure measurement opens up a world of possibilities, allowing us to gather valuable insights and control various aspects of our surroundings. And with the advent of microcontrollers like Arduino, this power becomes readily accessible to hobbyists, makers, and engineers alike. Arduino, a versatile open-source platform, provides a user-friendly interface for interacting with electronics, including pressure sensors. By connecting these sensors to an Arduino board, we gain the ability to measure and interpret pressure data, enabling us to create innovative projects and automate tasks based on pressure changes. Whether it's monitoring weather patterns, controlling industrial processes, or even building interactive art installations, Arduino pressure sensors offer a wide range of applications limited only by our imagination. This journey into the world of Arduino pressure sensors begins with a fundamental understanding of the different types of sensors available. Let's delve into the world of Arduino pressure sensors. These electronic components convert pressure measurements into electrical signals. These signals are then processed by the Arduino board, allowing us to interpret and utilize the pressure data. The choice of pressure sensor depends on the specific application and the desired level of accuracy, sensitivity, and response time. Analog pressure sensors produce a continuous output voltage proportional to the applied pressure. This analog signal is fed into the Arduino's analog input pins, where it is converted into a digital value using the board's built-in analog-to-digital converter, ADC. These sensors are well suited for applications requiring continuous pressure monitoring, such as weather stations or altitude measurements. Digital pressure sensors, on the other hand, provide a discrete output signal, typically in the form of a high or low voltage level, indicating whether the measured pressure is above or below a predetermined threshold. These sensors are often used in applications requiring simple on-off control based on pressure changes, such as detecting the presence of an object or triggering an alarm system. Force sensing resistors, FSRs, are a special type of pressure sensor that changes resistance based on the applied force. Unlike traditional pressure sensors that measure air or fluid pressure, FSRs are designed to detect force applied directly to their surface. This makes them ideal for applications involving touch sensing, such as interactive buttons, robotic grippers, and weight scales. Now, let's focus on analog pressure sensors, the workhorses of the pressure sensing world. These sensors provide a continuous stream of data that reflects the ever-changing pressure levels in their environment. Their ability to capture subtle variations in pressure makes them indispensable in applications requiring precise monitoring and control. These sensors operate on the principle of converting mechanical deformation caused by pressure into a proportional electrical signal. Typically, a diaphragm or membrane within the sensor deflects under pressure, altering the resistance of a strain gauge or the capacitance of a capacitor. This change in resistance or capacitance is then translated into a voltage output that corresponds to the applied pressure. The output voltage of an analog pressure sensor is typically linear, meaning that a given change in pressure results in a proportional change in voltage. This linear relationship simplifies calibration and data interpretation, allowing for straightforward conversion of voltage readings into pressure values. Moreover, the continuous nature of the output signal enables real-time tracking of pressure fluctuations, providing valuable insights into dynamic systems. Analog pressure sensors find widespread use in various fields, including weather monitoring, industrial process control, and medical instrumentation. In weather stations, they measure atmospheric pressure, a key indicator of weather patterns and potential storms. In industrial settings, they monitor pressure levels in pipelines, tanks, and reaction vessels, ensuring safe and efficient operation. Lastly, let's explore digital pressure sensors, which excel in applications requiring precise on-off control based on pressure thresholds. Their ability to deliver clear-cut signals, indicating whether a specific pressure level has been reached, makes them ideal for triggering events or activating alarms. Digital pressure sensors typically incorporate a pressure sensing element, similar to those found in analog sensors, but with an added layer of signal processing. This processing circuitry converts the analog pressure signal into a digital output, often a high or low voltage level, representing the on or off state. The threshold pressure at which the sensor switches between on and off states is usually programmable, allowing users to customize the sensor's behavior according to their specific needs. This flexibility enables the creation of pressure-activated switches, alarms, and control systems tailored to specific pressure ranges. Digital pressure sensors find applications in diverse scenarios, from simple everyday devices to complex industrial systems. In household appliances, they may control the flow of water in washing machines or detect pressure changes in refrigerators. In industrial automation, they can trigger safety mechanisms, such as shutting down machinery if pressure exceeds a safe limit. In Section 5, we delve into force-sensing resistors touch and beyond. Force-sensing resistors, or FSRs, are quite unique when compared to traditional pressure sensors. They are specifically designed to detect force applied directly to their surface. Unlike pressure sensors that gauge the pressure exerted by fluids or gases, FSRs react to physical contact, which makes them perfect for touch-sensitive applications. These sensors are composed of 2 layers of conductive material, separated by a thin, compressible spacer. When force is applied to the surface of an FSR, the spacer compresses, which brings the conductive layers closer together. This action reduces the resistance between the layers, leading to a measurable change in electrical conductivity. It's important to note that the relationship between applied force and resistance in FSRs is typically nonlinear. This means the change in resistance isn't directly proportional to the applied force. However, with proper calibration and signal processing, accurate force measurements can be achieved. FSRs are widely used in various applications such as touch sensing, force feedback, and weight measurement. For instance, in interactive displays and touchscreens, they enable pressure-sensitive input by responding to the force of a finger or stylus. In the field of robotics, they are crucial for providing feedback on grip strength and object manipulation. Moving on to Section 6, we explore Arduino pressure sensors in action within weather stations. Weather stations are essential tools for monitoring atmospheric conditions and rely heavily on pressure sensors to provide crucial data on barometric pressure. This data is a key indicator of weather patterns and potential storms. By integrating pressure sensors with Arduino, DIY enthusiasts can create their own weather stations capable of tracking changes in barometric pressure and offering valuable insights into local weather dynamics. Analog pressure sensors are commonly used in these stations due to their ability to provide continuous pressure readings. The sensor's output voltage, which is proportional to the atmospheric pressure, is fed into the Arduino's analog input pin. The Arduino then converts this analog signal into a digital value using its built-in ADC. Once the pressure data is digitized, the Arduino can process and display it in various ways. It can output the readings to an LCD screen, store the data on an SD card for later analysis, or even transmit the readings to a computer or smartphone via Wi-Fi or Bluetooth. By combining pressure sensors with other environmental sensors, such as those for temperature and humidity, comprehensive weather stations can be created. These stations are capable of providing a complete picture of local atmospheric conditions. Moreover, these DIY weather stations offer a hands-on way to learn about meteorology and explore the capabilities of Arduino in environmental monitoring. Section 7. Taking to the skies. Altimeters with Arduino and pressure sensors. Pressure sensors play a crucial role in altitude measurement, enabling the creation of altimeters, devices that determine an object's height above a reference level. By leveraging the relationship between atmospheric pressure and altitude, Arduino and pressure sensors can be combined to build DIY altimeters for various applications, from model rockets to weather balloons. As altitude increases, atmospheric pressure decreases. This inverse relationship forms the basis of barometric altimeters, which utilize pressure sensors to infer altitude based on measured pressure changes. Analog pressure sensors are well suited for this task due to their ability to provide continuous pressure readings, enabling real-time altitude tracking. The Arduino receives the pressure data from the sensor and converts it into a digital value. Using a known pressure-altitude relationship, the Arduino can then calculate the corresponding altitude based on the measured pressure. This altitude information can be displayed on an LCD screen, stored for later analysis, or transmitted to a remote device. Arduino-based altimeters offer a versatile and cost-effective solution for various altitude measurement needs. They can be incorporated into model rockets to track their flight path, integrated into weather balloons to monitor their ascent, or even used in drones to maintain stable flight altitudes. Section 8. The Industrial Advantage: Automation with Pressure Sensors. Pressure sensors play a vital role in industrial automation, enabling the monitoring and control of various processes based on pressure changes. By integrating pressure sensors with Arduino, we can create custom automation solutions for a wide range of industrial applications, from regulating fluid flow to ensuring safety in high-pressure systems. Digital pressure sensors are often preferred in industrial automation due to their ability to provide clear-cut on-off signals based on pressure thresholds. These signals can be used to trigger events, activate alarms, or control actuators such as valves and pumps. For instance, a digital pressure sensor can be used to monitor the pressure in a pipeline. If the pressure exceeds a predetermined safety limit, the sensor triggers an alarm and shuts off a valve to prevent potential damage or hazards. Similarly, a pressure sensor can regulate the flow of liquids in a tank by controlling a pump based on the measured pressure level. Arduino, with its flexible programming capabilities, allows for the creation of sophisticated industrial automation systems tailored to specific needs. By integrating pressure sensors with other sensors and actuators, we can develop intelligent systems capable of monitoring multiple variables, making decisions based on real-time data, and automating complex industrial processes. Section 9. Understanding Sensor Interfaces: Key to Effective Arduino Projects. While Arduino provides a user-friendly platform for interacting with pressure sensors, understanding sensor interfaces is crucial for effectively integrating these sensors into Arduino projects. Each type of pressure sensor communicates with the Arduino using specific protocols and signal characteristics, which must be properly understood and implemented for accurate data acquisition and control. Analog pressure sensors typically output a voltage signal proportional to the measured pressure. This analog signal is fed into the Arduino's analog input pins, where it is converted into a digital value using the board's built-in ADC. Understanding the sensor's voltage range and sensitivity is essential for configuring the Arduino's ADC and interpreting the resulting digital readings. Digital pressure sensors, on the other hand, communicate using digital signals, often in the form of high or low voltage levels. These signals are typically connected to the Arduino's digital input pins, where they can be read as high or low logical states. Understanding the sensor's output voltage levels and communication protocol is crucial for interpreting the digital signals and triggering events based on pressure thresholds. Force sensing resistors, FSRs, exhibit a change in resistance based on the applied force. This resistance change can be measured using a voltage divider circuit, where the FSR forms one leg of the divider. The Arduino then reads the voltage across the FSR, which reflects the applied force. Understanding the FSR's resistance range and calibration is essential for interpreting the voltage readings and converting them into force values. Section 10. Conclusion: Mastering the pressure points of Arduino. Pressure sensors, combined with the versatility of Arduino, open up a world of possibilities for monitoring, controlling, and interacting with our physical environment. From weather stations to altimeters to industrial automation systems, Arduino pressure sensors empower us to create innovative projects and solve real-world challenges. Mastering the pressure points of Arduino involves understanding the different types of pressure sensors, their characteristics, and their interfaces. Analog pressure sensors excel at providing continuous pressure readings, ideal for applications requiring precise monitoring and control. Digital pressure sensors shine in scenarios demanding on-off control based on pressure thresholds, triggering events or activating alarms. Force-sensing resistors, FSRs, stand out with their ability to detect force applied directly to their surface, enabling touch-sensitive applications and force feedback systems. By grasping the nuances of sensor interfaces, we can effectively integrate pressure sensors into Arduino projects, ensuring accurate data acquisition and reliable control. This understanding allows us to harness the power of pressure measurement, unlocking a realm of creative possibilities and practical applications limited only by our imagination. As we continue to explore the ever-expanding world of Arduino and pressure sensors, we empower ourselves to innovate, automate, and interact with our surroundings in increasingly sophisticated and impactful ways.